Chapter 4 is quadratic functions and equations. Big ideas with this chapter have to do with equivalence, functions, and solving equations and inequalities. As far as equivalence goes, what are the advantages of quadratic functions in vertex form and in standard form? For functions, how is any quadratic function related to the parent quadratic function y equals x squared? And for solving equations and inequalities, how are the real solutions of a quadratic equation related to the graph of the related quadratic function? Those are our essential questions and big ideas for this chapter, things you should be able to answer by the time we get through it. Section 4.1 is quadratic functions and transformations. I can identify and graph quadratic functions, learning target for this section and what we're shooting for. Big ideas here. The graph of any quadratic function is a transformation of the graph of the parent quadratic function, y equals x squared. The vertex form of a quadratic function is f of x equals a times, in parentheses, x minus h squared plus k. The axis of symmetry is a line that divides the parabola into two mirror images, and it's found at x equals h. X equals tells us that that is a line. Okay, here we have the line x equals h. The vertex of the parabola is hk, the intersection of the parabola and its axis of symmetry. So this h value here matches the h or the x value of our vertex because it's where the parabola and the axis of symmetry intersect. Okay, very similarly to how when we did absolute value, the vertex and the axis of symmetry intersected at that point as well, and our axis of symmetry and our h value were the same. A parabola is the graph of a quadratic function, and we can write it in the form f of x or y if you want to equals ax squared plus bx plus c. If you look at the take note on page 194, here it has the parent quadratic function. And it says the parent quadratic function is going to be f of x or y equals x squared. It's a parabola. A parabola, remember, is that U-shaped graph. It can either be up or down depending on some characteristics, and we'll talk about that here in a bit, but it's a U-shaped graph. And we get that U-shaped graph, okay, with our table of values. -2, -1, 0, 1, and 2 for our x's. -2 squared gives me 4. -1 squared gives me 1. 0 squared is 0. 1 squared is 1. 2 squared is 4. So our parent quadratic has a point at -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. The two branches of this U-shaped graph are symmetric, which means they reflect upon each other. Left branch would land on the right, right branch would land on the left. Its axis of symmetry for the parent function just goes through x equals 0, and our vertex right here is at the point 0, 0. So our parent function, we're centered at 0, 0, with our axis of symmetry being x equals 0, and our two branches going up symmetrically on both sides. In example 1, we're going to graph a compression or a stretch, and we're going to do this very similarly to how we did with absolute value. So we're going to start off with our parent function. So at -2, 4, I have a point. -1, 1, I have a point. 0, 0, I have a point. 1, 1, I have a point. And 2, 4, I have a point. So again, my parent function looks like this. It's a U-shaped curve, okay? It's a curve, not straight edges, and it keeps going out forever, okay? It doesn't loop back in, so be careful with that. These don't have to be perfect. I'm going to be mainly focusing on your points, because as you can tell, my two sides aren't perfectly symmetric either. So we're going to be focusing on your points, but should be curved and head outward instead of coming back in. If it comes back in, it's not a function. Fails our vertical line test. Now, here we have a half that's being multiplied. And remember from when we did absolute value that anytime we have something multiplied by a value, it's going to be a stretch or a compression. This one is a compression because half is less than 1. So that deals with the value of our function, our outputs, our y values. So we look how far away we are from our vertex. At 1, right now, I'm 1 unit away. I take that value and multiply it by my compression factor, and I get a half. So my new point is going to be at the same x value, but only half for my y value. Same idea here. I look at my point. Originally, for my parent function, it's 4 units away from that vertex at 2. Okay, I'm 4 units up. I take that and I multiply it by my compression factor, and I get 2. So my new point has the same x value, 2. My vertex stays where it was. On my left branch, my point was 1 unit away. I take that and multiply it by my compression factor and get a half. My new point is half of a unit away. And my last point here, at -2, I'm 4 units away from where my vertex is. I multiply that by my compression factor. And now my height is just 2. So again, the same x value, so still at -2, but my height above my vertex is only 2. So when I connect these dots, again with curves that go out, this is the graph of f of x equals half x squared. It's been compressed, which means it's been smushed down a little bit to look like our parent function, just smushed. Now feel free to pause here and give this a try if you'd like. We want to know what is the graph of f of x equals -1/3 x squared. So the negative, remember, we talked about this with absolute value, means it's going to be reflected across the x-axis. So now it's going to open down. We're going to go down. So my original parent function is still y equals x squared because it's quadratic, x squared. -2, 4, -1, 1, 0, 0, 1, 1, and 2, 4. And again, that comes from -2 squared, -1 squared, 0 squared, 1 squared, and 2 squared. So my parent function, I missed that point a little bit, but looks something similar to that. Here, we know we're going to go down instead of up because of the negative. So I look at my heights. Right now I'm 1 unit up. I take that and multiply it by my compression factor here, which is 1/3, and I get 1/3. Instead of going up 1/3, I'm going to go down 1/3 because, again, I have that negative, that reflection. So at my same x value, instead of going up 1, I'm going to go down 1/3 and be at 1, -1/3. My vertex stays in the same place. On the right side, my second point used to be 4 units up in my parent function. I take that and multiply it by my compression factor. And it works the same way if this would have been a stretch. If it would have been more than 1, it would have been a stretch, and it works the same way. We do the same thing. Here, I get 4/3. Remember, we're going to go down instead of up because of our negative. 4/3. So instead of going up at 2, I'm going to go down 4/3, or 1 1/3. Okay, same thing on the left side. At -1, my point is 1 unit up. I take that height, how far I am away from my vertex, multiply it by my conversion factor, and now I go down 1/3. At -1, I go down 1/3 to -1/3. And my last point here, right now I'm 4 units up. Okay, the value of that point is 4 higher than the value of my vertex. Multiply by my conversion factor, and I get 4/3. Again, instead of going up, we're going to go down 4/3, or 1 1/3. We connect these. Remember, it's going to be a curve. And there we go. Take note on page 195, deals with reflections, stretches, and compressions. Here, it shows pictures of our reflections, which we just dealt with. Instead of going up, it's down. So instead of having a happy face parabola, we have a sad face parabola. And that happens based off our a value, so the number in front of our x squared. If a is positive, we have a happy face parabola. Okay, the y-coordinate of the vertex then is the minimum value of our function. Right here is our vertex. It's the lowest value, remember the value is our output, our y-coordinate, that our function will ever have. So we have a minimum, and it's our y-coordinate of the vertex. If a is negative, we have a sad face parabola. It opens downward. The vertex then becomes the maximum, the highest point, and it's still that y-coordinate of our vertex because we're talking about a maximum value, okay, the output of our function. What is the maximum our function is going to give us out? And here, that's the y-coordinate of our vertex. If a is negative, sad face, we have a highest point, our maximum. If a is positive, happy face, we have the minimum, and that's our y-coordinate of our vertex as well. So in example 2, we're going to graph translations of quadratics, and then figure out how each graph is a translation of our parent function. So we could do these with a table of values, but because we've done translations before, we can figure out what these are going to be, just like we did with our absolute value. Right now I have a negative 5 on my x squared. That means we're going to take the value of our function x squared and subtract 5 from it, which is just like taking our parent function here and subtracting 5 from each point, which means it's a vertical translation down 5 units. So I take each of these points, move it down 5. Keep in mind it's symmetric. So if we move our point that's 2 over 5 units, we have to move on both sides. So our function for g of x looks like this. Okay, it wants to know, how is each graph a translation of the parent function? Well, g of x is the graph of our parent function, y equals x squared, translated vertically down 5 units. At b, for h of x, we have a minus 4 on the inside. Remember, we're looking for the height that would give us an output of 0 again to find our vertex. So here, x is 4 minus 4 gives me 0 squared 0. So I'm going to move to the right 4 until I get to 4. Anytime it's right, it's going to be minus on the inside. Right and minus. Okay, so I'm going to move each point right 4. Just like we did with absolute value. Okay, it's like what I have to do to my function in order to get back to where we started. Starting at 0, 0. Okay, in order to get that same output, I have to go right 4 to 4 to get an output of 0. We can connect our branches here. And that is our function. Our x value changed there, and we remember that because it's inside, it changed our parentheses. So h of x is the graph of our parent function, translated horizontally. 4 units right. And I'll continue in another video.